Okay, so in the second part, we're going to talk about the notion of convergence for measures. And in particular, what I want to do is define weak star and narrow convergence of measures. And then after that, I'll tell you what it means for a family of measures to be tight. So let's get started. So the first thing is how does one make sense of convergence of measures, right? It's a very abstract concept, and let's try to make some guess. So, so what does it mean for mu n to converge to mu, as n goes to infinity? So what does it mean for a sequence of measures mu n to converge to mu, right? And so you can guess, perhaps try to come up with some definitions, and these are some natural definitions that you might try. So for instance, you might come up with something like this, right? And so what you want is that for all sets in your sigma algebra, let's just say that it's the Borel sigma algebra, you want this sort of continuity property that, for all, every time you evaluate mu n of A, you want it to be equal to mu of A. In particular, the good part about this definition is that it preserves mass, right? And so if mu n are probability measures, then mu is also a probability measure, right? And why is that? Well, simply just put x here, then mu n of x is 1, and the limit of a constant sequence is just itself. And so in particular, you get mu of x is also mu of x is also 1. So this is an advantage of this definition. And then you might also, try to mimic something that you see for convergence of a sequence of functions. And in particular, you might look at the distance between the measures, right? So you might be tempted to do something like this. You might want to look at, for all A, I'm just using the Borel sigma algebra, but then, you can define this for arbitrary sigma algebra. And here you want to perhaps look at the distance between the sequence of measures evaluated at the set A minus mu of A. And you want this quantity to actually become small, right? You want it to go to 0 as n goes to infinity. So these are two possible definitions that you could try. And unfortunately, they are too restrictive, and I will show you why that's the case. So if we go to a new page. Now, let's look at a very simple example. In particular, let's take mu n to be delta 1 over n, right? So these are Dirac masses, and this means that if the set contains 1 over n, then you will get 1, otherwise you get 0. So, you can just define it for natural numbers, right? And so ideally what you would expect is that, this guy converges to the Dirac mass evaluated at 0, right? This is natural. This is what you would want. But unfortunately, you don't get this, right? Because if you take, for instance, the set containing 0, then observe that mu n of A will be 0, whereas mu of A is 1. And so the distance between these guys is not actually becoming 0 as n goes to large, it's 1. It's at least 1. And so this definition definitely fails, because this soup is at least bounded below by 1. And of course, this definition also fades, because if you put the mu n of the set containing 0, will evaluate to 0, because 0 is not contained, the set 0 does not contain 1 over n for any n, whereas mu of A will be 1. So you can see that both of these definitions fail, and so we need something better. So then you might be tempted to try something that you see when you study more functional analysis. You might want to try some sort of weak star convergence, right? So this could be interesting. So let's see. So here we define weak star convergence. Okay, so So for mu(n) to converge weakly, what this means is that this will happen if for all f which are continuous and compactly supported, we have that the integral actually goes to d mu. And so this happens when n goes to infinity. So this is the definition of weak star convergence, and it seems promising. In particular, it's in some sense, I would say it's less restrictive as compared to these definitions, but again, it has a drawback. And the drawback is that, notice here that we could easily claim that if mu(n) were probability measures, then mu would be a probability measure. But if we use this notion of convergence, then that's not necessarily true. And here's a quick example that will demonstrate that. So let's say that the space that you're working in is R, and the sequence of measures that you take is delta k. Then just take any testing function f, which is continuous compactly supported. What you get is that the integral of f with respect to this measure, well, it's a Dirac measure, so it just evaluates the function at that point. And because your function is compactly supported, this actually will go to 0 as k goes to infinity. Well, if you're not familiar with what it means to be compactly supported, I'll just give you a little picture. So the idea with saying that a function is compactly supported, it just simply means that there's some compact set in which the function takes non-zero values, and outside that set it just becomes 0. So of course, when you go to infinity, the function has to be 0, and that's why f of k actually goes to 0 as k goes to infinity. So what you can see is that this limit is actually converging to 0. So in particular, what must happen is that f of d mu must be 0, and this happens for all f that are compactly supported. And actually, this implies that the measure must be actually the trivial measure. And so you can see that even though mu k were themselves probability measures, mu is not. So this is unfortunate, and so maybe we have to work harder and come up with a stronger notion of convergence. And this is exactly what narrow convergence will provide us with. So definition. So here you have narrow convergence. And so here, instead of taking functions that are compactly supported, what you want to take is functions that are continuous and bounded. So you say that mu(n) converges narrowly. Let's just say that if the integral of phi, if for all phi that are continuous bounded, we have d mu of n going to phi d mu, and this happens as n goes to infinity. So we just made a slight change. Instead of taking functions that are compactly supported, we took functions that are bounded, right? And so immediately, at least one thing, we wanted to rectify this flaw that, that even though the probability measures, even though we have a sequence of probability measures, it's possible that the limit might not be a probability measure. And so let's just check that if we face the same problem here too. Of course, just a spoiler, we don't, and you can verify. So maybe this could be a remark. So remark. So if you just take phi to be just identically 1, then notice that this is not compactly supported, right? It's 1 everywhere, but it's bounded, so it's a valid testing function, right? So just compute mu k of x. So mu k of x we know is 1, right? So in particular, it's just the integral of d mu k, right? This is just by definition, right? But then this guy is will converge to 1 of d mu, right? This is a valid testing function, and we know if you have a sequence, so if you have a sequence mu k that is converging narrowly to mu, then then for all testing functions you must have this identity, and in particular you choose a testing function which is 1, you plug it here, you know that this converges by this assumption to the integral of 1 over the space x with respect to the measure mu, but this is nothing but mu of x. And we know, so in particular, if mu k of x was 1 for all k, then mu of x will be 1 also. So this is good. This shows that we are making some progress. And the next thing that I wanted to introduce is perhaps something that will be useful later. So let me just conclude this by saying that mu is in p of x if mu k in p of x for all k in n. So the next thing that I want to talk about, just define this for the moment, and then we'll make sense of it later, is the notion of a tight family. And so what's the motivation for this, right? So here you see that if you look at the definition of weak star convergence here, the thing is that it's possible that some mass may actually escape to infinity. And that's something that we don't want. And in order to do that, what we need some sort of notion of compactness in order to prevent that from happening. And that's why we need to define some sort of family that captures that idea. And this is precisely the motivation for defining a tight family. And so you take a collection of measures, of probability measures, and then you say that is tight. This family is tight if for any epsilon positive you can find a compact set k of epsilon, of course it's a subset of x, such that when you take the measure of x minus k, then this can be made arbitrarily small. And of course, you have to ask yourself, where does mu come from? Well, mu is of course a member of your family. So again, just to reiterate, a collection of probability measures is tight if for all the measures in the family you have this property that given any epsilon, you can find a compact set such that the complement of that compact set can be made arbitrarily small. So there's a very nice relationship between all of these notions. We'll combine them later in the next video.